Hello, everybody. Welcome back. Today we're going to be looking at the first part of Unit 8.4, which talks about acid-base reactions. I'm not going to do all of Unit 8.4 in one video because it's quite a bit of material, so I'm going to do it in two different parts, and this is going to be part one. So let's get started. All right, so the concept we're going to be looking at in this video is on the concept of titration. And we have actually seen that word. We looked at the concept of titration back in Unit 4. We very briefly spoke about titration curves, a concept called the equivalence point. And when you all eventually at some point get to do a titration in the lab, what you would do is a situation like we're seeing in this graph. You can see that the base is what's being added. So let me familiarize or remind you of the terms analyte and titrant. So this graph is showing us that the base is the thing we're progressively adding more and more of. That is our titrant, which must mean that the acid is our analyte. Okay, and that's one type of titration, is acid plus base. Okay, let's review what the term equivalence point means. Okay, equivalence point is the point at which where you know how many moles of one of the pieces that you're dealing with, either your analyte or your titrant, usually the titrant, and you can use stoichiometry to solve for the moles of the other one. Now, for what we are going to be doing, ladies and gentlemen, the equivalence point is going to be a simpler definition for that, because acid-base reactions are always going to be stoichiometrically in a 1-to-1 ratio. We can assume that the equivalence point means the following. However many moles of acid we have is also the number of moles of the base. That's where that prefix equivalence comes from. Equal what? Equal moles. Okay. I did not say that to you back in Unit 4 because we were doing titrations not just of acids and bases, but also redox titrations. And so truly equivalence point means one reactant is, equivalent based on its molar ratios, but in terms of acid-base reactions, because our reactants are always going to be in a 1-to-1 ratio, we can think of it as moles of acid are equal to moles of base. Now, before we get into any of the math, I want to refresh your memory of a little mnemonic device that I used in a previous subunit. I think it was 8.3 maybe. Okay. We did a whole bunch of ice table problems back in Unit 8.3. And I introduced this memory trick to you, what I call Womex problems, because all of these reactions we kept writing again and again always seemed to have water as one of the reactants. And we set up our ice tables, and we filled in the information into the ice table. The numbers that we were putting in there were molarities. And in those ice tables, we were adding, subtracting, and solving for X. So they all had these commonalities again and again. All these ice table problems I made you do, those were all Womex problems. Well, what we're going to see today is a new type that I call Newman problems. I know this seems silly, but it's helpful, I think. And we're not going to see reactions with water as a reactant anymore. We are going to see, this is hard writing vertically, we are going to see neutralization reactions. Remember what that term means back from Chem 1? Neutralization means acid plus base. We are going to set up ice tables, but they're going to look a little different because they're not going to have molarities in them anymore. They're going to have numbers of moles put in them. And we're not going to be adding and subtracting X anymore. We're going to be adding and subtracting actual numbers, which, ladies and gentlemen, is good news for you because if you'll recall, when we did Womex ice tables and we had to solve for X, we did a lot of graphing in our calculators and finding the intersection point to find X. We're not going to have to do that anymore. In what I call Newman problems, you won't have to graph at all. Okay, so let's look at an example of a titration situation, okay? And what we're going to start off with, guys, is the simplest type of titration, which is strong acid plus strong base. A situation maybe like this. So we have a set amount. We have 40 milliliters of 0.2 molar, and that is perchloric acid. Ladies and gentlemen, get in the habit. Anytime you come across an acid or a base, ask yourself, is this a strong or a weak acid? Is it a strong or a weak base? It's always good to identify what are you dealing with here. Perchloric acid is one of our strong acids, and we're going to be titrating it with potassium hydroxide, which is one of our strong bases. So we have a set amount of acid, that's our analyte, and we're going to be adding progressively more and more strong base. And what we are tasked with doing, it says, calculate the pH after the following volumes of base have been added, 0, 10, 40, 80, 100. Okay, so I'm going to sort of talk you through the thought process here, and we're going to go kind of slow at first, but then you're going to start to pick it up a little quicker. So let's start at the beginning. It's a very good place to start. Okay, so right here, 0. Now that doesn't mean I have 0 of anything. It just means we haven't added any base yet. The only thing we have is our perchloric acid. That's it. So let me get to a fresh screen and let's be good little chemistry students and continue this habit of writing out the major species. We always have water. And let's review, how do we write a strong species in a list? We don't write them as an entire compound. Perchloric acid is a strong acid, which means it's going to dissociate completely. So I'm not going to write HClO4. I'm going to write it as H plus and ClO4 minus. I'm going to separate them because that's what strong acids do. And guys, let's review. Let me go back to the slide. Think back to an earlier subunit. How do you find the pH of just a strong acid and nothing else? Well, if you remember, the molarity of a strong acid is also going to be the molarity of H plus because of that complete dissociation. And then it's real easy to find your pH. So let me get back to my screen here. Okay, so 0 milliliters of base have been added. So what do we do? Super quick and easy. pH equals negative log of the H plus concentration, which is the same thing as the molarity of the acid. And I can do that because it's a strong acid. And we'll go to 3 decimal places. And there's my first answer. And I want you to get in the habit, ladies and gentlemen, of asking yourself, does my answer make sense? And look at that pH. That's a very low pH. But it should be, because think about it. All we have is strong acid and nothing else. It should be very acidic. So this answer does make sense. So we've taken care of the first volume of base added, which was 0. Now we're ready to move on to 10 milliliters of base have been added. Okay, so now we do have some base on the scene. Guys, we need to update our major species list. It's a strong base, so they completely dissociate. So look at my list now. Okay, so now we're ready to move on to 10 milliliters of base. I want you to look at the list of major species, and this is practicing a skill we've done before. I want you to look at this list and pick out the best choice for the acid, the strongest acid in the list, and the strongest base in the list. And hopefully you remember you want to pick H plus as your acid. Why? This is a term you can quote me on. It's the king daddy of acids. H plus is the strongest acid, so I'm definitely going to pick that one. What am I going to pick for the base? I'm going to pick OH minus. Why? Because OH minus is the king daddy of bases. It's the strongest. And what product do we get? We get H2O. So I want you to look at this reaction here, guys. In fact, look in particular at your reactants. Okay, please notice water is not one of my reactants. This isn't a Womex problem. Oops, that's not what I meant to do. Let's try that again. This is a Newman problem. I did not choose water as one of my reactants. This is a neutralization, and we are going to set up an ice table. However, it's going to look just a little bit different, okay? Just like the Womex problems back in Unit 8.3, we are not going to care about water. Water is a liquid. It's never going to be part of the equilibrium if there is one, so we're just going to ignore it. Remember what I said, this middle M is moles, not molarity. So the moles are what's going to get put into this ice table. So let's go back to our slide. H plus is my first reactant. Where is it coming from? It's coming from here. I need moles. And look at the two pieces of information you have here, ladies and gentlemen. You have molarity and you have a volume, so you can get moles. Okay, now you're probably thinking, okay, I need to change that 40 milliliters, I need to change that into liters to 0.04 liters, and if you do that and you do your math, you will get this number. Okay, and that's going to be the moles of H plus. Now, if you would like to write that value into your ice table, go for it, okay? You're absolutely welcome to do that. I am not, okay? That decimal bugs me, those zeros bug me, so watch what I write. And you don't have to do this. Some people like this, some people don't. Instead of writing 0.008 moles, here's what I'm going to write. 8 millimoles. Ladies and gentlemen, I did not say millimoles, okay? Milli, like the prefix milli, millimoles. I personally find the number 8 easier to deal with, and here's another thing. I want to tell you guys that most of the volumes that you'll be given in these problems will be given to you in milliliters. To get millimoles, I don't have to change milliliters to liters. I can just do 40 times 0.2 and I get 8 millimoles. I like that better. It's less work. It's a nicer number to deal with. But guys, if that makes you uncomfortable, you don't have to do it. You can put in 0.008 moles and you'll be fine. Okay. Let's figure out moles or millimoles, your choice, for the base now. Now, where is the base coming from? It's coming from here. Here's the molarity, and here is our volume. Okay, if you do the math, you'll find that you have 0.001 moles. But if you're willing to come along on this journey with me of millimoles, then I'm going to write this. Okay, you think you don't like millimoles now, I'm going to work on converting you. Okay, you'll come around, don't worry. Okay, all right. Now, this third N in Newman, we're not going to be adding and subtracting X. We're going to be adding and subtracting actual numbers. Now, what number? Well, here's the deal, guys. I am circling OH minus because I can look at this and I can see that OH minus is going to be my limiting reactant. I know that because these reactants are in a 1-to-1 ratio and I have less hydroxide. Remember, guys, what it means to be a limiting reactant. It means that the reactant that will completely run out at the end of the reaction. So how did I get from 1 to 0 in that hydroxide column? Well, I must have subtracted 1. And guess what? I'm going to subtract 1 here as well. So you're always going to subtract the smaller number of moles or millimoles because that's going to be your limiting reactant. So at the end of this reaction, I have no hydroxide left. The only thing I have left is H+. Now guys, keep in mind, what are we trying to figure out here? We're trying to find the pH. Remember the formula for pH. pH is equal to negative log of the H+ concentration. Well, that's not a concentration. That is a number of moles, but I can get it. Watch this. This is slick. Millimoles divided by milliliters equals molarity. Okay, usually we say moles divided by liters equals molarity, but if I'm in millimoles, millimoles divided by milliliters gives me molarity. Now, what volume do we divide by? 40 plus 10. So 50. Let me come back over here. So my H+ concentration is 0.14 molar. And at this point, guys, all I have to do to find the pH is now plug that molarity in. And I get this, 0.854. Okay. Now, let's take stock of what we've just done. Okay, I want you to, in particular, focus your attention on what the pH was up here and what it now is. Before we added any base, the pH was 0.7. When we started to add a little bit more, notice the pH has gone up. Now, has it gone up a lot? No, it hasn't. But if you'll remember, let's see, oh, there we go. Look at this initial part of the graph here. Does the pH go up? Yes, it does. Does it go up a lot? No, it doesn't. It creeps up. The initial part of an acid-base titration is usually very slow. The pH does change, but it's slow. Okay, and that's exactly what we're seeing. So we've done the first two. What I want you guys to do is pause the video and set up the next addition, this 40 milliliters. I want you to set up the next addition yourself and see if you can solve it. The reaction is going to be the same. It's still going to be H plus OH minus yields water. Okay. The amount of the acid is not changing. Okay. Think each one of these additions of base is like a separate problem. Okay. We have a set amount of acid that's given to us right there. So that's not going to change. The only thing that is going to change is our amount of base. I want you to complete that ice table and see how you do. I'm going to work it out, but you're welcome to pause the video and try it on your own. Okay, how'd you do? Exact same reaction, same amount of acid. The only thing different was the amount of base. And if you'll notice, guys, the pH has again gone up. Has it gone up a lot? No. Let's go back to look at the other. It started at 0.7, it went up to 0.85. Now it's up to 1.3, but again, that first part of the titration is it creeps up slowly. Okay? Now, this part of the titration has a special name, and I want you to write it down. This point in the titration is called the halfway point, or sometimes it's called the half equivalence point. Okay? Halfway to what? Well, I just said it. It's halfway to the equivalence point. And what that means is, guys, if you look at this, we had this amount of acid. We had 8 millimoles of acid. Do you agree that I have added enough base to neutralize half of that acid? That's what the halfway point means. It means halfway to the equivalence point, but it also means half of your analyte has been neutralized. Okay, So when you can see that you're going to be cutting your analyte in half, and you can tell that right by the first line of your ice table, you'll know, yep, I'm at the halfway point. Okay. So the next addition is 80 milliliters. I want you to set this one up for yourself and see if you can solve it. I'm going to work through it and write all the work out, see how you do. Okay. You may have gotten to this point and said, I can't find the concentration of anything. I don't have anything left over. And you're absolutely right. You don't. There is no limiting reactant. All the acid and all the base have been completely reacted. There is no leftover H plus. There's no leftover OH minus. The only thing present is water. So guess what the pH is? The pH is going to be exactly 7. Okay. And this, ladies and gentlemen, in case you hadn't already guessed, is our equivalence point. Okay. Remember, in terms of acids and bases, equivalence point means, let me change color here, moles of acid and base will be equal. Okay, that's not what happens in a redox titration. That means it's related through stoichiometry, and so does this, but since these are in a 1-to-1 ratio, they're equal, we are at the equivalence point. And I want to go back to that graph, okay? And you'll notice that this graph is showing us that the equivalence point, the point on the graph, the most vertical inflection point, is at a pH of 7. In case you're wondering, is the equivalence point for a titration, is it always at a pH of 7? And the answer is no, not always. However, if you are doing a strong acid plus strong base titration, then the answer is yes. It will always be at 7, okay, but only if it's strong, strong. Okay, there's one more addition of base that I want you all to set up at with 100 milliliters. I'm going to work through it. Feel free to pause the video and see if you can solve it on your own, but I'm going to write it out as well. Now in this one, guys, since the acid was the limiting reactant and I have excess hydroxide left over, I've got a hydroxide ion concentration. Probably what the easiest thing to do would be to find the pOH first, which is the negative log of the hydroxide ion concentration. And I get this for the pOH. Remember, to get pH, it's just 14 minus that number. So we end up with this. And that number makes sense. I have excess hydroxide, so my pH should be above 7. So let me go back to that graph one more time. Okay, so what we saw was, as we were adding more and more base, the pH was creeping up. It was going up, but slowly. All right, we hit the equivalence point, or excuse me, the halfway point. And then when you get closer and closer to the equivalence point, adding very small amounts of titrant can cause the pH to increase pretty dramatically, very quickly. We hit the equivalence point, and then we continued to add more base, and that gave us an excess of hydroxide. So anywhere before the equivalence point, we would have leftover H+. Anywhere beyond the equivalence point, we have leftover OH-. And so I've shown you essentially all of the possible situations that you could see with a strong titration when you're asked to actually calculate the pH. So what I want to show you now, this is the last thing we'll do in this video, is just kind of a sample question that you could see on the AP exam. It's a multiple choice question. I want you to try to do it without a calculator because that's what it's intended. But this is a strong situation, so give it a try. All right, so because this acid and the base are strong, okay, we could go through the writing out our major species situation and we would come up with the same net ionic equation that we did in the example we just went through. Okay, and again, this is multiple choice, but we can do this, I promise you. So it's a Newman problem. I can tell that because there is not water as one of my reactants. So let's focus on finding number of moles of each piece. Okay, H+ is going to be coming from nitric acid here. And you might say, well, we don't have a calculator. How am I supposed to do this? Well, volume and molarity, you multiply them to find moles, or in this case, because the volume is in milliliters, let's go with millimoles, okay? I promise you this can be done without a calculator. Here's how I think of it, guys. If you're not good about multiplying with decimals, think about just what is 30 times 3? Well, that's 90. But it's not 30 times 3. It's 30 times 0.03, which is a difference of 2 decimal places. So guess what? Move it back 2 decimal places. So that's 0.9 millimoles. Okay, so I'm going to fill that in my ice table down here. 0.9 millimoles. Okay, let's do the same thing with the base. Again, this is kind of how I think of it. What is 70 times 2? Well, that's 140. But it's not 70 times 2, it's 70 times 0.02, so that's 2 decimal places smaller. So that's 1.4 millimoles. So let's fill that in our ice table. See, the math is not as hard as you think it is. Okay, I can see this is going to be my limiting reactant. That's going to leave me with some excess hydroxide. Okay, we are supposed to figure out not only which is the limiting reactant, but what the pH is approximately. And so now that I know that the acid is the limiting reactant, I can eliminate answer choices A and B. But let's see if we can figure out approximately what this pH is going to be. And think about what you would have done, just like in the problem we just finished. I would divide this 0.5 millimoles by the total volume, which is 100 milliliters. Let me bring this over here. So that's going to leave me with this. Okay, now, if you're thinking, well, still, I mean, I've got to do logarithms with this. How am I supposed to do this without a calculator? Don't leave that 0.005 written like that. Write it like this. 5 times 10 to the negative third. And guys, remember, when you are estimating, when you take the negative log of something in scientific notation, your answer is going to be very close to that exponent. But so if it was 1 times 10 to the negative 3, the POH would be exactly 3. But because it's 5 times 10 to the negative third, the POH is going to be 2 point something, something, something. Well, if the POH is 2 point something, 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 that means the pH is going to be 11 point something, 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 which, ladies and gentlemen, allows us to circle D as our answer. That is the closest number to the true answer. The answer in the calculator comes out to be like 11.7 or something like that. It's approximately 12. So is this a lot for them to ask you to do in multiple choice? Yes, but it can be done. So I just wanted to show you an example problem. Okay, so that is our first look at some titration calculations, and that is the simplest type. Strong plus strong is always the simplest. In the second part of this unit 8.4, I'm going to cover what do you do if you've got a weak acid or a weak base in the mix, and that can get a little bit more complicated, and that's why I wanted to do that in a separate video. So I hope you have learned a little something today, and I look forward to seeing you next time.